All right, so continuing on our overview here, 6.5 I think is probably one of the most interesting sections that we cover in the Laplace transform, and that's because it introduces that weird function, the Dirac delta function, that is actually not a function in the normal sense. It's a generalized function, and so kind of intuitively we see the delta function as being zero everywhere except at time c, and then infinity, I'll put that in quotes, if t equals c, because that's not really a value, right? You can't assign the value of infinity to the function. Okay, but what's really interesting about this delta function is not only that we have this property here, but that we also have the property that the integral of the delta function is not zero, which you might expect, but it's equal to 1. And that makes it very useful in terms of the Laplace transform. And so the second big principle, or the big usefulness of the Dirac delta function, is that if you take the Dirac delta function and you multiply it by f of t, what do you get? Well, you get 0 if t is not equal to c. So this zeroes out the function everywhere except times c. And so this is really just delta of t minus c times f of c. So you're kind of isolating f at a point, and then here you can work with your delta function. So just as the reason I'm bringing this up is because if you take like the integral from minus infinity to infinity of the Dirac delta function times f of t, what do you get? Yeah, you just get f of c, and that's very interesting. So this is used to model a short duration force like that, but it has only a finite strength. And so, yeah, these can be very, very interesting. We also see that if I differentiate, should I actually write this down? I hesitate. Will people mock me for saying this? Derivative of u sub c of t is equal to the Dirac delta function at time c. Yeah. This is weird because the Heaviside function we don't usually think of. Well, it's not differentiable at c in the usual normal case, but you can kind of see the reasoning behind this expression here, right? Because it's 0 everywhere, and then at c you have a vertical line here, and the slope of a vertical line would be infinity. So it does make sense that you would be able to write this. You would not be able to prove this in the usual sense, though. We would have to. You can do it with the Laplace transform, but and that's why we're kind of bringing this up now. So this is more general than our normal functions. Good. So yeah, so Dirac delta function is very, very strange object in our undergraduate career. Good. So what was the other thing that we were going to touch on in chapter 6? I think it is something called the convolution. And so this was an operation between two functions, f of t convolved with g of t. Good. And then we should be able to define that. I better use the same notation as the notes. So you could use tau, or you could use other variables for your definition, but I'll just go ahead and write that as f of t minus u times g of u du. And so just as a, sorry about that. So just as a point of reference here, when you integrate this u out, u is running from 0 to t. You've already got an f of t in there. So what's going to happen is that this does become a function of t that comes out. So the convolution between two functions of t is another function of t. And this looks kind of weird. Remember in the video on this, what we said is this is a flip. You can think of it as flipping your function over, multiplying it by g, and then summing the result across. This is also a shift. So you're shifting by u, and then you're flipping, or is it it's a flip and a shift. Yeah, a flip and a shift, and then you multiply by your g. Yeah. This is, again, a very interesting function because it's used in so many different places. This is just the one-dimensional version of the convolution, but there is a two-dimensional version as well. We won't get into that, but yeah, it can be used in a lot of different places. So our main goal here is to use the convolution in the convolution theorem. The convolution theorem. And that just says that the Laplace transform of a product, inverse, let me go backwards, inverse transform of a product is the convolution. Okay, and so that helps a lot with inverting a product. Now I should say, like we said in the notes before, you can only use this theorem when it's explicitly stated that you can. In other words, if I ask you to invert 1 over s minus 1 times s minus 3, I don't want to see you writing e to the t called with e to the 3t. Okay, I want you to actually use partial fractions to work that out. Okay, so good. We're not using the convolution for much else. You should be able to compute the convolution for simple functions and then use the convolution in certain inverses. And we looked at those in the exercises. So just to give an overview then of Chapter 6, Laplace transform. We have new functions. The new functions were the Heaviside function, the Dirac delta function, and the convolution. And then we had techniques for inversion of the transform. And so again, that was multiply and divide by the same number. We talked about those in the last video. Yeah, and so the Laplace transform turns out to be a very nice technique for solving differential equations. I guess I didn't do any specific examples here. Kind of waiting for the review, but if you do have questions from the homework, let me know. This was just a quick overview of Chapter 6.